Welcome to this lecture, the lecture on ballooning, the first lecture on ballooning. And the last time we ended with discussing, or basically I ended with asking you, what are the 3 physical principles to fly? And today we're going to talk about ballooning. And clearly this is the first principle in which you can defy gravity to generate an upward force by being lighter than air, float on air. For instance, by using helium or hydrogen or hot air. This creates ensures that your overall weight is less than the air. And in this way you can fly. But there are 2 other ways in which you can fly, in which you can generate an upward force. The first one of these 2 other ways, and when you're heavier than air, basically the 2 ways to fly heavier than air, are by pushing air down. Because we're going to talk later about pressure around wings and aerodynamics. But if we zoom out a little, a wing also pushes air down. And similarly, a rotor is of course something that clearly pushes air down. So by creating this momentum of air going down, we can create our own momentum to go up. And this of course also hints at the third way in which you can generate lift, is push anything else down. For instance, a rocket lifts off by pushing the fuel, by burning the fuel and pushing this down. And in this way creates as a reaction the force upwards, and this is also a way to fly. Well, we'll follow in our course these physical principles, but we also follow history. And the first principle in which we flew was the principle on the left here, by being lighter than air. Because in the previous lecture I called the 20th century the century of flight, but humans were able to fly before the 20th century, well before the 20th century. In fact, the balloon itself was already invented in the 3rd century, and this is the Gongming lantern. It's a Chinese invention, a hot air balloon. It's still being used at festivities instead of fireworks, if you will, send it upwards. And I've tried it myself once at the New Year's Eve. I think it's also responsible for many UFO sightings because it's something that's lit when it flies. It's a very nice sight. And it was originally invented also for military purposes. For instance, to signal something to troops far away. And according to some sources, it was also used for surveillance somehow. And I do not really see how this worked, whether this would light a certain area which allowed you to see enemy troops or some other principle was used. But surveillance and communication were the 2 applications which are mentioned for these balloons. But later, much later, in the 18th century, this was used for manned flight. And here we're still 120 years before the 20th century. So well before the Wright brothers. There were 2 other brothers, the Montgolfier brothers. Surprising that in both cases it were brothers. In the old days, sometimes people called 2 men that were living together brothers, while they were not really brothers, but the Montgolfier brothers and the Wright brothers were really brothers. And they are also sides of a character which together work really well. One of them very creative and many ideas, and the other one more orderly and structured and trying to see whether it was really possible and calculated. And this combination often works very well. Their father had a company in paper, wallpaper if I'm correct, and their first prototypes were indeed made of this wallpaper indoor and showed the principle that it was possible with hot air to fly, even though they themselves thought it was not hot air, but it was some specific gas which came out of fire, which was lighter than air, which allowed them to create lift. And after these indoor experiments, they increased the volume and had ever more experiments outdoor. And one example, which was really the one but last flight before they really started achieving manned flight, was one where they used animals to experiment. They used a duck, a rooster and a sheep, as you can see on the slide here. And this was the demonstrations were by now already drawing large crowds. And this was a famous demonstration which was done to demonstrate that it was safe for humans to fly. And these 3 animals were not a random selection from the nearby farm. They were in fact part of a scientific experiment. They were, among other things, not just worried about what the vehicle would do, but also what the effect of taking off from the Earth would be on humans. Would it still be possible to breathe? Would it be possible to live higher than what we are normally used to? And they thought maybe there was some layer of oxygen which would follow the curvature of the Earth, which would allow them to breathe in mountains, but perhaps not when you leave the Earth. So they chose the duck because the duck is a flying bird, and this should always be able to breathe and live. And if the duck would die, then something was wrong with the vehicle. It was not due to altitude. The rooster is then a bird which doesn't fly, which would show whether it's bird physiology, which allows you to live higher in the atmosphere, or whether it is due to being used to be at higher altitudes. That was the difference between the duck and the rooster. And then the sheep, not being a bird but a mammal, was of course the model human. If the sheep would survive, then humans would probably survive. So this was the final flight before manned flight, and then it was proposed to the king to start a demonstration of manned flight. The king then proposed to get some prisoners, because prisoners would be, they are dispensable. You can get new prisoners when the experiment fails. And the king thought this was a good idea to have prisoners as first test subjects for flight. But then a physician and a military general proposed to be the first ones to fly. And they thought it was very honorable to be the first one to fly, and they were the first one to fly. And in fact, one of them, Rogier, was a pioneer which extended his knowledge of ballooning for the remainder of the day. He was a famous pioneer in those days. And ever new inventions were done with ballooning. And for a long time, people thought that the future of flying would be ballooning. And this was still ongoing in the 20th century. Think of the Zeppelins. Here we see the Hindenburg, a huge Zeppelin and able to cross large distances, used for passenger travel. And people thought this was the future of flight. It was like this for more than 120 years. Well, in the 20th century, of course, we also saw aircraft taking off. But it was still not clear what would be the future way for air travel. And I think one of the things that really destroyed the image of Zeppelins was the disaster which happened in 1937 in the United States, close to New York, when a fire destroyed the Hindenburg. In fact, one of the problems was that this Zeppelin was filled with hydrogen instead of helium, because Germany was suffering from a lack of helium, and hydrogen is even better at generating lift. And this ignited and created a huge gas explosion, and then also the paint on the cloth of the Zeppelin caught fire, and this created this huge disaster. I personally think that even without this disaster, balloons would not have made it instead of aircraft as normal means of transport, because there is a good reason why it's better to use aircraft. And this is also important to remember nowadays, that sometimes, as a green alternative for aircraft, these types of airships are proposed again. Well, they work very well for specific purposes, but they will never replace aircraft. And why would you want an airship? Well, if you want to be in one position, and it's good to use an airship because it generates lift for free. You don't need to burn fuel all the time to stay in the air. And another advantage of ballooning in general is that if you use, for instance, helium or hydrogen, you can get really high. A weather balloon can get higher than an aircraft. But there are clear disadvantages. The huge volume that you need for balloons means that they generate an enormous amount of drag as soon as you have some forward speed. And this means it only works if you fly really slow, because if you fly fast, as drag increases quadratically with speed, you will have to burn a lot of fuel for moving something through the air, despite the fact that you get the lift for free. Well, because the history of flying started with ballooning, we also start exploring the principles of flight with ballooning. And this area of aeronautics is called aerostatics. So in spite of aerodynamics, where we are moving through the air and the air is moving around the aircraft, we first look at generating lift while you aren't moving. And this is called aerostatics. We have a number of questions for you to ask yourself, and hopefully you will be able to answer all of them after the course on aerostatics. So, first question, we see both types of balloons, both helium and hot air balloons, still flying today. So, which one provides more lift? And if you think about the helium balloons, you might think of party balloons. Well, if party balloons also generate lift, how many party balloons can you safely carry before coming airborne? This, if you know aerostatics, you will be able to calculate it. Another question is, if we have a balloon, take for instance this party balloon, it's easy to understand. We look at this party balloon, its volume remains constant. It doesn't get larger or smaller. At a certain time, it keeps its volume. And this is because the forces inside and outside are in equilibrium. So the balloon doesn't get larger, doesn't get smaller. There's an equilibrium of forces along the surface. Well, if there's an equilibrium of forces along the surface, why does a helium balloon then go up? How does it even know what is up to begin with? And final question is, how could you calculate what altitude you can reach with a balloon? For these questions, you need to know the principles of aerostatics. You will be able to answer these questions when you know aerostatics. Before we start looking at the laws which govern aerostatics, we have to look at the gas law. This plays an important role in aerostatics, obviously. And the gas law you may have learned in this form. Pressure times volume equals the number of moles times the gas constant, and I've used a strange R here, but I will explain later, times the temperature in Kelvin. And this gas law is something you probably have learned in high school. It's used for many purposes. It's a very useful law, but not for us. Because if we are going to look at aerostatics, at the atmosphere, and at large volumes, and at moving air along a streamline, we want another type of gas law. We do not always, when looking at the atmosphere, we do not know the number of moles in the atmosphere or the number of moles that we want to look at. The volume, we need to define a bit of volume every time. So ideally, we would not want the volume or the number of moles to be present in this formula. So the first thing we're going to do is to derive a gas law without these two, if you will, annoying variables, the volume and the number of moles. We will use the volume occasionally in the balloon, when we talk about the inside of the balloon, but especially when we talk about the atmosphere, we'd like to get rid of it. And for this, we have a different gas law, which we will derive starting our normal gas law. So the universal gas law is pressure times volume is equal to the number of moles times the universal gas constant, which I draw as a sort of curly R, times the temperature in Kelvin. It's not exactly the law that we want. We said we want to get rid of the volume and of the number of moles. So if we look at the volume, what other laws do we have with the volume? Well, the density, we know, is mass divided by volume. And this means that we could also write volume as mass divided by density. And density is a quantity which has a value also if you do not know about how much air you're talking. This is more a state variable. You can talk about the density at different positions along a streamline, for instance, or in or outside the balloon. So this would be good. But we still have the mass here now, which would still make things annoying, as we again would need to know what the amount of air is to talk about the mass. Well, for the mass, we know that it is the number of moles times the molar mass. The molar mass is the mass of one mole, one specific amount of molecules, the number of Avogadro, and N is the number of moles, so the total mass is this number of moles times the molar mass. And this also shows that for N we can write this is the mass divided by the molar mass. Well, this is something that would really help if we use this equation and this equation to replace N and V with this other variables. Let's see what we get then. So we say pressure times volume, but instead of volume we now write mass divided by rho, by the density. This equals the number of moles, but for that we write the mass divided by the molar mass. And then times the gas constant and the temperature, and this remains unchanged. What we now see is that we have the mass on the left and right side of the equation. So if we divide both sides by the mass, we get a different equation, which has now become independent of the amount of air that we're talking about. The pressure divided by the density is the gas constant divided by the molar mass times the temperature. And we can also write this as pressure, the P, this should be the P, pressure equals rho times R divided by the molar mass times temperature. And a special trick now becomes that if we talk about a certain gas, then this remains constant, and we call this our specific gas constant. And for this we use the normal letter R. In other words, we can write our gas law now as P is rho R T. And when we talk about air only, we will use this gas law a lot. And here the R, if you calculated what it actually is, the molar mass of air is 28.97, and then dividing the normal, the universal gas law by this results in a specific gas constant for air of 287.00 per kilogram Kelvin. And this is in fact the gas law which we will use most of the time in our course. This gas law is called the equation of state, in contrast with the normal universal gas law with which we started the one here. This is a universal gas law with the universal gas constant. This is the equation, the lowest part is the equation of state with the specific gas constant. P is rho times R times T. When we talk about balloons, we still have to deal with different gases. So there we will occasionally use this version of the equation of state, where we do remember that RR is actually the universal gas constant divided by the molar mass. So this equation of state we will now use to see how balloons actually generate lift. So in the next video clip you will see the lift calculation for different types of balloons.